Okay, let's talk about quantifiers in this video. While dealing with the types of sentences, the four types of sentences that we had, we came across some open sentences. They were declarative sentences, but we couldn't classify them as statements because they were open. If you use quantifiers with open statements, they become with open sentences. I'm sorry, they become statements. So you can say whether they are true or false if you use quantifiers, and we call those statements as quantified statements because once they were open sentences, but if you use quantifiers with that sentence, it becomes a quantified statement, and we can talk about its truthness or falseness after that. So there are two kinds of quantifiers, the universal quantifier and the existential quantifier. This is like the upside A symbol for the universal quantifier and the backwards E symbol, kind of a backwards E symbol for existential quantifier. So, and you can think of these two as the hyper versions of and or. So when you use the universal quantifier, uh, for example, I've done it over here for all x, y in real numbers, and I had my open sentence here: x plus y is equal to 5. If I didn't have this, this would be an open statement, open sentence: x plus y is equals to 5. But if I use this for all universal quantifier for all x, y in real numbers, then this becomes a statement, and this will be a true statement if this open sentence is true for all x, y in this possible range over here, the real numbers. So if you think about this, it's not true, right? For all x and y in real numbers, this does not hold because you have x and y like 1 and 2, which do not add up to 5. So this is a statement, but it is a false statement because it doesn't hold for all possible values of x and y in the real numbers. On the other hand, if you have this other quantifier called the existential quantifier, this is true if you have just one possibility where this is where your open sentence is true. So if you have some x and y in real numbers, for this statement is true, then this whole statement is true. And then we know that there are there is at least one pair of x and y. You can have x is equals to 1 and y is equals to 4. You can have many more else, but if you have one x and y, one possibility of x and y where this is true, then this using this existential quantifier says that this whole statement will be true. I hope you understand. You can compare this with the or and the and statements that we studied in the last video. So if you have this open sentence being true for all possibilities, only then it's true. Otherwise, if any case it's false, then the whole statement becomes false. On the other hand, the existential quantifier says that if you have at least one possibility where it's true, then that whole statement is true. So okay, I have more examples. Let's talk about those examples for you. There exists x belonging to real numbers such that x squared plus 1 is equals to 0. Now, this statement is not true because there is no real number if you take the square of that number and add 1 to it, you get 0. Because if you were to solve this, then you would get something like x squared is equals to minus 1, and x is equals to plus or minus the square root of minus 1, which goes into the realm of imaginary numbers, complex numbers. So there is no real number which satisfies this sentence. So I can say this is a false statement. If I had just this much, then this would be an open sentence and we couldn't talk about its truthness or falseness. But if I had this, existential quantifier, I can say whether it's true or false based on where my range is for x. Now, instead of real numbers, if I had, let's say, the set of complex numbers, if I replace this with a set of complex numbers, then yeah, then this becomes a true statement because we know there is a complex number I whose a square, if you take, it becomes -1, and if you add 1 to it, it becomes 0. So if I had this, instead of real numbers, I had the set of complex numbers, then this would be a true statement. If it were the real numbers, it would be a false statement. Next example says for all x in the set of natural numbers, x by 2 is in the natural numbers, and if you are saying that this is a true statement, then you need to be sure that it is true for all the x in the natural numbers, and we know for odd numbers, x by 2 doesn't come out to be a good natural number. It comes out to be some point decimal value, some fraction. So I wouldn't say this is a true statement. This is in fact a false statement. So as a side note, I can say that if you want to say for a universal quantifier, a statement involving the universal quantifier is a false statement, then you just need to give one example where it's false. If you want to say that it's true, then you need to show that it is true for all the x in the possible range. So here I can say that there is an x, namely equal to 3, let's say, for which this is not true. 3 by 2 is not a natural number. So I can say that the whole statement is false. Next we have this for all x in this set 0, 1, x squared is equals to x. Now, if we have a small range, a small set of possible values here, only 0 and 1, and if you plug 0, it indeed it becomes equal to the square, because 0 square is equals to 0. And if you plug in 1, 1 square is also equal to 1. So for all possible values of x, this is true. So I can say this is a true statement. Next, we have there exists x in the set of natural numbers such that x squared is equals to x. And if you want to show that this is a true statement, then you just need to come up with one example where this is true, because it is asking for just existence of at least one element. And we know that the set of natural numbers has one such element, namely x is equals to 1, whose a square if you take, you get the same number. So I can say that this is a true statement. So you can have a lot of open statements and try to check whether they are true or false if you use either the universal quantifier or the existential quantifier.